Okay, so over here you can see this is a layout, the general layout of the project in a city. Okay, so as I said, the type of bridge, the type of pier, the type of girder, everything has to be specified by the client. All right. So if we've got like public works department of any state in India, which is like, for example, it is planning for having a metro station in Chennai or maybe in Mumbai. So this authority must give you a design basis report. So what is a design basis report? So this report is, you can say that is the single most important report before you begin any sort of designing. So this is typically a report which specifies everything that the project would actually require in order to find its completion. So before starting any project, a well-defined design basis or a design requirement criteria, in addition to a well-defined scope of work, has to be set forth by the client. So this client, he must tell you exactly in this report, what is this project, where it starts from, what is the scope of work of the contractor or the detailed designer, and what type of a project are we looking up to at? Is it a cable stayed bridge? Does it also have extra doors bridges? In between, do we have a span which is curved? Do we have girders which are made up of steel, or do we have only concrete girders? What type of launching method is used? What type of formwork is supposed to be used? Okay, so this documents the rationale, the criteria, principles, assumptions, constraint used for the detailed design engineering and the final designing of this product. Okay, so this document must provide you with all the principles of design. It should also specify what code you should follow, what is the grade of the concrete that is going to be used for the pier, for the foundation, for the pile foundation, for the pier cap, what is the type of bearing, is it a neoprene bearing, is it a pot PTFE bearing, if we have got multi-cell box girders, what is the what would be the geometry of this design of this girder? Everything it should specify. Okay, so it is essentially a set of conditions, requirements, needs of the project, and performance criteria. Okay, so this should include concrete and steel grades, type of girders, construction methodology, what are the tolerances, what is the section geometry. For example, if you have got piers, what are the aesthetic they should share with you the visualizations, the concepts, the test required, load cases and combinations. Yes, this is also an important point. All the load cases, they will specify, okay, we need a load case, and your design should specify or satisfy this certain load case. Your design should comply with this codal load cases and combinations. They'll say, okay, whatever you design, the combination should be used from American code. The combinations should be used from this certain code. So the designers has to comply with the DBR 100%. Okay, it is the responsibility of the detail designer to comply with everything on the DBR. Okay, it will also specify the permissible speed of the metro bogie. Okay. Okay, so as I told you that over here, that in order to have a proper idea of what the ground below this structure looks like, we need to have multiple surveys. So one of the surveys is having a soil bore log. So soil boring is a practice of geotechnical investigations, the purpose of which is to determine soil load bearing capacity. Okay, so this will help us understand what is the chemical contamination below. Does the rock start quite early, or if the rock is too deep inside? Where is the water table? What type of soil? What type of soil are we dealing in? So it provides key pieces of information like bearing capacity, type of soil, cohesive soil, is it a non-cohesive soil? Where is the water table? Lithology is the study of rocks, the rock profile. So over here, once we have the survey done, it will give us a report like this. So before proceeding in designing anything, the soil bore log should be at hand. All right. So this is the bore log at only one location. Maybe like, for example, over here, if we saw, these are so many different piers. So let us say, okay. So let us say this is the bore log of location PB3. Okay, so what this basically tells us is that the, over here is the depth of ground level. So what this basically tells us is that the ground below PB3, okay, up till 1 meter, it is mixed pebbles. Okay, below it,
Excuse me, sir.
Yes.
Sir, the screen sharing is on.
It is stopped. Okay.
Yes, sir. It's stopped.
Now it's okay.
Yes, sir.
All right.
Yes, sir.
Okay. All right. So what this basically tells us, okay, like for example, if this is a bore log for location PV3, I've taken it from over here. Let us say this location. Okay, we are okay. As of now, we are trying to design this pier. All right. So we need to know the exact conditions below this this pier. So what we'll do is we'll go to the soil bore log, and basically what this log tells us is that just below PB3, the ground up till 1 meter is mixed pebbles. After that, for another 1 meter, we have got sandy clay, and then for 2 more meters, we have got clean sand, and below that, it is all coarse sand. So this gives us an idea as to what would be the safe bearing capacity. Also, there'll be one more. There will be many columns, but one of the columns would be SBC. It will tell us what is the SBC and what would be the design SBC. So they will maybe tell us, okay, at this location, use SBC 250. Okay, so this would be a third-party concern. We as structural engineers are not required to go into a lithology. This will be done by a third party, and it will be given to us directly. Okay, so this will enable us to design foundations, and even if we are designing a open foundation, it is very important. SBC is very important. And this helps us understand what is the strength of the soil below, what is the bearing capacity of the soil below. All right, so moving further, this is a typical sketch, or you can say a typical elevation of what a metro viaduct looks like. So as I've indicated, there are different parts to it. Okay, this being the transverse side. Okay, this is the transverse section. This is the longitudinal section. So over here, what we have used is a multi-celled box girder. And this is actually, this has been taken from a live project. Okay, so for obvious reasons, I cannot share the drawing with you. So I've made a sketch for you people. So basically coming from bottom to top over here, we have used pile foundations. Okay, in order for the load to be distributed properly, we'll have to use a pile cap. Just below the piers, we'll have a crash barrier. What is the role of crash?
Excuse me, sir. Good evening, sir. This is which is the more better? This is a multiple box girder or single cell? I mean, which is more, because in the normally it is said in the construction that single cell is more compatible and as well as the easy to construct. So
that is
just
right.
kindly.
That is right. Okay, but it is better that we take questions at the end so that I can be in a streak of explanation. But still, multi-cell box girders, of course, it is much more difficult. Multi-cell box girders are usually used when we have got multiple tracks. Okay, like for example, we've got a wide viaduct. Okay, we've got a huge bridge. If the width of this girder has to exceed a certain limit, we'll have to use multiple cells. Like for example, these are called as cells. Okay, so if for example over here, this is track 1, this is track 2. So if I need to have more tracks over here, maybe if I have track 3, so it would not be accommodated. So maybe I'll have to go for a wider girder. This is the wing wall. Okay, so I'll have to have a larger cantilever over here. So if I have only 2 tracks which can be accommodated on this level, so I don't have to go for a additional cell. So I can directly have a single cell box girder. Okay, so of course multi-cell box girders are more difficult. Okay, secondly, as we were discussing, crash barriers. So the role of crash barriers, we'll deal with this when we are talking about loads. Okay, This typically is the pier. As I said, the DBR has to specify what is the shape of the pier. Is it a circular section? Is it exactly rectangle? Does it have chamfered edges? Is it maybe does it have multiple piers? Everything has to be specified by the DBR. Even this architectural curve, every aesthetic element has to be specified by the client itself. Okay, of course, the detail designer can say, okay, the capacity is not matching, so maybe I'll have to change the section. Of course, you can change it. Over here is the pier cap. Okay, this is section, the section that is coming like a flanging section. Okay, so this is called as a pier cap. It's a bearing. Bearing is one of the most important aspects, and hopefully, if you have another session on detailed design, I'll shed some more light on what sort of bearings are used for what sort of spans. Okay.
So bearings, sir, we require the spherical or in this normal pot and pot PTF?
Well, that depends upon what sort of restraint you want, what sort of support condition you're trying to have. Okay. So most possibly, when we are having a simply supported span, it is going to be either a neoprene or an elastomeric bearing. Okay. This is rather an important and unique phenomenon of the piers. This is a seismic arrestor. What these seismic arrestors actually do, we'll discuss in later slides. This is the box girder, multi-cell. This is the left-hand side span and the right-hand side span. These are crash barriers, or crash parapets. These are rail pedestals. In a moment, I'll also show you a 3D model so that it will be much more clear. This is a bit more detailed sketch. Okay. One of the main concerns of a designer when he's actually trying to design, or when he's actually trying to transfer the forces to the bottommost part of this structural arrangement, is that he needs to know what are the different levels. All right. So over here, I've marked these. I've marked all the important levels that you need to consider. Okay. So I'll also let you know why these levels are important. So if you can see over here, I believe, okay, this is clear, right? Okay. So from over here, if you see, this is the top of pier. As I told you in the previous slide, the pier stops over here. Okay. Now this is the pier cap. So this is the top of pier level. This is the centroid of the pier. You need to know this. Top of pier cap, top of the pedestal, okay, and the top of bearing. Centroid of the girder. What is the level of the centroid of the girder? Okay, because if you've got any moment, it is actually rotating about this centroid. Top of deck, top of rail. Okay, what is the rail? This is the rail upon which the axle load is going to be directly incident. So you need to know what exactly is this level. And the center of bogie. Bogie is the metro, you can say metro rail. So what is the centroid of this bogie? Okay. Apart from that, some of the other levels is like centroid of the vehicle. Why do we need a centroid of the vehicle? Is because, as you know, this is a crash barrier. Okay. So when a vehicle is going to hit this crash barrier, we need to understand at what point is the force centered as to what is the point that is centered around, so that we can calculate the moment and the force impact. Top of pile cap, bottom of pile cap, and pile cutoff level. This is the point at which we stop the pile. Mostly this is stopped when we encounter a rock. Okay, or if it is a friction pile, then maybe it is a different case. Okay, also, if in case your structure happens to be in the vicinity of a water body, or it is assumed that maybe in this zone there is a threat of having excess rain, or the water is it is anticipated that it is going to experience waterlogging, or there is a river besides it. So it is important for us to know that what is the low flood level and what is the high flood level, and also what is the ordinary flow level. Okay. So, but if we have got, but if you're designing structures which are not threatened by water, you don't need to consider this. We can have a dry analysis. We don't have to consider a wet condition. Okay. All right. So I'll show you a 3D model of a pier. Okay, so this is a model that I created in Shaper 3D. This very much indicates everything that you can have in a typical pier. Okay, so as you just saw, the arrangement comprises of piles, pile cap, crash barriers, the pier cap. Okay, so this is the pile and the pile cap. Coming up, it is a crash barrier. As of now, this is a circular section for the pier. Okay, then the pile cap, and above it is the assembly for bearing. And the red member that you see over there is the seismic arrestor. Okay, and the holes that you see over there are the holes for sleeves. Okay, these 4 holes that you see, these are sleeves which are given in order for the launcher to fix itself. Okay. So we can have different pier sections. As I said, it is the requirement of the client completely as to what is the type of pier he wants. All right. So in this site, the pier assembly that you see, these are the piers that were typically used in many parts of Mumbai Metro and Pune Metro. If you see over here, this is a pier, the crash barrier, and a post tension pier cap. Over here are the cables, if you can see. I'll show you in a moment. And these are U girders. Okay. And we can have any number of variations, and we can have different shapes for piers, as long as you can structurally prove it, as long as you can structurally validate it. All right, so this pier over here, what you see is that the pier has been casted and the reinforcement has been left in order for this precast pier cap to be fixed upon it. So if you see over here, the pier is a separate entity. It has not been monolithically constructed. The bars have been left in order to achieve fixity between the pier cap and the pier. So this is the 3D model of the pier. And later on, the pier cap has been lifted and simply placed upon it. Okay. So this is rather a unique case that we had encountered in Mumbai Metro and Pune Metro as well. So what you see in front of me is a rather simplified sketch of what we did. And if you see that we have got 2 different types of girders. One is a box girder on the right hand side. Another one are a batch of concrete I-section girders. So they are both hosted upon the same pier cap, and this is a cantilever pier cap. By cantilever, what I mean is that if you see, this portion is rather elongated, and it's like it is under the cantilever behavior. Okay, and we've got different types of piers. We've got RCC piers, we've got piers with post tension pier cap, we've got hammerhead piers, cantilever piers, something like this, portal piers. I'll show you what that is, and coming down with station piers. Station piers. So basically, while we were designing this, I'll show you what we encountered as a challenge. So if you see over here, this is a sketch that indicates post tension pier cap. I've taken a longitudinal section for this. Okay, so over here is the pier zone. Okay, okay, over here is the pier zone. You see, this is the pier zone indicated by dotted line. After here, this zone is the cantilever zone, and as you saw over here, this portion, these 2 bearings, they are holding a box girder. They are holding a box girder, and these 1, 2, 3, 4 bearings are holding I-section girders. So all the weight, all the moment, everything that is that this deck is actually experiencing have to be transferred by the way of the girders to the bearing. Okay, so bearing is the central interface between the superstructure and the substructure. Okay, so these 4 I-section girders, okay, incident upon them, these are the load values or moment values or horizontal force values which are incident upon this bearing, and this is the seismic arrestor. Okay, over here. So if you see over here, I've tick marked 3 point load, but I've crossed this 4th one.